Hello and welcome to lecture 42. In last lecture, we were discussing about the mixed flow turbofan engines. Let us take one numerical in order to understand how do we do the cycle analysis for mixed flow kind of configuration. So, data available are this is for sea level condition, where a Mach number it is 0. So, you can say that is what is the initial takeoff kind of configuration. The temperature and pressure are 298 Kelvin and 101.325 kilopascal. Fan pressure ratio is 3.85. So, let us try to understand this number. When I say 3.85, so you must realize this is not by single fan, it is with multi fan configuration. So, per stage pressurized for the fan, that is what is limited in the range of maybe from 1.2 to 1.8. Most modern high bypass ratio engines, they are having say this fan pressure ratio in the range of 2. So, you can say this is multi fan configuration. Next, it says the compressor pressure ratio is 8, bypass ratio is 0.25. Now, you can say this number it is less than 2, that means it is low bypass ratio configuration. So, when we say low bypass ratio configuration, you just realize this configuration what we are discussing, it may be from say fighter engine. Yes, it can easily be guessed. Next, we have is turbine entry temperature is 1520 Kelvin. Total pressure loss in combustion chamber is 3%. Total pressure loss during the mixing process is 2%. The heating value for the fuel is 42,800 kilojoule per kg. The total engine mass flow rate is 80 kg per second. The isentropic efficiency for different components are say 98% for diffuser, for fan it is 88%, for compressor it is 86%, combustion chamber the efficiency is 97%, for turbine the efficiency is 91%, for nozzle the efficiency is given 95%, and it says like take mechanical efficiency to be 98%. Cp value for the air as well as for hot gas they are given, and we need to estimate the velocity from the nozzle. We need to calculate what will be the thrust specific fuel consumption, say thermal efficiency, propulsive efficiency and overall efficiency. So, let us try to look at this. Very first thing, what all information is given to us, we will try to put say this on TS diagram. So, you can say here this is what is representing what all components they are given with. So, be careful what is given, and accordingly you just try to put the TS diagram, put this numbering. Let us discuss how do we proceed with. So, let us say what is a hint for solving this numerical. We have our first component as say intake or say diffuser. For that the Mach number is given, it is say 0. My temperature and pressure at the entry it is given, diffuser efficiency is given. Based on that we can calculate what will be the V infinity and exit pressure and temperature from the intake. The next component we have is our fan, and for fan the pressure ratio and efficiency for the fan they are given. So, based on that we can calculate what will be the exit pressure and exit temperature from the fan. We have our next component as a compressor, and for compressor the compressor efficiency and compressor pressure ratio that is given to us. So, from that we can calculate what will be the turbine what will be the temperature and pressure at the exit of our compressor. Be careful here in this numerical, no information is given in terms of bleed. This kind of engine may have bleed as per the requirement. So, if it is given, then you need to change, you need to modify your calculation accordingly. Be careful. Same way here we have our combustion chamber. For this combustion chamber we will be having drop of pressure. We know what is our turbine entry temperature, calorific value, burner efficiency. Based on that we will be calculating what will be the pressure and fuel air ratio. Next component we have is our HP turbine, and for HP turbine the efficiency is given, mechanical efficiency is given, say maximum turbine entry temperature it is given. So, based on that we can calculate what will be the exit pressure and exit temperature from the HP turbine. We have our component that say LP turbine. For this turbine we have information about the turbine efficiency, mechanical efficiency, and from there we are able to calculate what will be the pressure and temperature at the exit of LP turbine. Now, here we have our component to be mixing. So, we can say mixing chamber or mixing process. For that this mixing ratio it is given to us, and based on that we can calculate what will be the exit temperature and exit pressure from this mixing chamber. Once we have all this information, we can do our calculation for the nozzle. The logic will be similar. We are given with say nozzle efficiency, and based on what will be the exit from this mixing chamber, that will be the entry condition for the nozzle, and from that we will be calculating what will be the critical pressure. This critical pressure, that is what will be helping us to decide what will be the exit pressure from this nozzle, and we can calculate what will be the static pressure, what will be the static temperature, and what will be the exit velocity. Once we have all this information, we can calculate what all will be the performance parameters for this cycle. Okay. So, let us put this in terms of the line diagram. As I told, maybe we will be having 2 or 3 stages of the fan, that is why it is written say fans. We have compressor, combustion chamber, HP turbine, LP turbine, mixing chamber and nozzle. And this we already have discussed in earlier class, just go through it again and you can understand here we need to solve this cycle in a systematic way. So, let us try to start from very first component. The component what we have is our intake, and for this intake the information given is M infinity is 0. Static pressure and static temperature they are known to us, and diffuser efficiency is given 98%. So, since my M infinity is 0, so we will be having velocity, flying velocity, that is what will be 0, and based on our diffuser efficiency correlation we can calculate what will be the exit pressure from this diffuser. Since my Mach number it is 0, so you can say my exit pressure will be same as my entry pressure, it is 101.325 kilopascal. Similarly, we can calculate what will be the temperature. Here in this case also, since my M infinity value is 0, so you can say exit temperature is 298 Kelvin. So, this two information that is what is available with us. We will be going with the next component. Our next component it is say maybe fan, or we can say fans. For this fans we have our pressure ratio to be 3.85. So, we can calculate what will be the exit pressure from this fan, and this exit pressure is coming as 390.1 kilopascal. Now, what we know, my temperature ratio that can be correlated in terms of my pressure ratio and efficiency. Since we have our pressure ratio known to us, this pressure ratio is 3.85 and fan efficiency is 88%. That is the reason I can calculate my exit temperature, and this exit temperature is 457.11 Kelvin. Now, as I told earlier, be careful what numbers are given, whether the fan isentropic efficiency is given or polytropic efficiency is given. Accordingly, this formulation will be changing. Since we are having multi-stage configuration, that is the reason we need to be very careful here. Maybe my first stage will be having some polytropic efficiency, my second stage will be having some polytropic efficiency, third stage may be having some polytropic efficiency, or maybe they all will be having same polytropic efficiency. So, just go revisit week 2 where we have discussed about the polytropic efficiency, and based on those polytropic efficiency how do we calculate our fan efficiency or maybe isentropic efficiency, both for fan as well as for compressor. So, be careful about these aspects. So, let us see what next we have is our compressor, and for this compressor our pressure ratio is given 8 and compressor efficiency is 86%. Based on the compression ratio, we can calculate the exit pressure from the compressor. It is 3120.81 kilopascal. In line to what all we have done for fan, we can write down our temperature ratio in the formulation of pressure ratio as well as the isentropic efficiency. If we are putting these numbers, what all we have in terms of T03, pressure ratio, efficiency, we will get our exit temperature to be 888.41 Kelvin. So, this will be the exit temperature from our compressor. Now, what we have as our next component? We know we have our next component at is say combustion chamber, and for this combustion chamber we are given there is a 3% loss of total pressure. So, that is what will be giving us idea about the exit pressure from the combustion chamber, and that if we are calculating, this number is coming 3027.19 kilopascal. Okay. Now, in order to calculate what will be the fuel air ratio, we can take the control volume of combustion chamber, we can put what is my heat input, it is m dot core into H04, that is what is the exit from my compressor. This is my amount of fuel what we are injecting into calorific value into burner efficiency. So, this will be my heat input, and at the exit of my combustion chamber I will be having m dot core plus m dot f at 0.5, means because of this combustion process we will be having the rise of temperature or rise of total enthalpy. Okay. So, now let us put this energy balance equation, that is what will be giving us idea about what will be the fuel air ratio. This fuel air ratio based on what numbers we know, Cp value for hot gas it is 1200, Cp value for air it is 1005, temperature values are known to us, calorific value of the fuel also is given. So, if we will be putting all this number, it says my fuel air ratio is coming 0.0235. Okay. Here let me put the point again. Suppose say it says we are not having any information about turbine entry temperature, but the given information is fuel air ratio, then accordingly you need to use this equation for the calculation of turbine entry temperature. So, do not get confused with these aspects. Okay. Now, let us move towards the next component. The component we have is our HP turbine. This expansion process we are correlating, it says my HP turbine it is used to rotate the compressor stages, and we have our mechanical efficiency also. So, let us put this work, turbine work is m dot core into 1 plus f Cp delta T0, that is what is equal to m dot core Cp delta T0. If we are balancing this, we will be getting say the exit temperature from this turbine, and this exit temperature is coming to be 1159.88 Kelvin. Okay. Now, in order to calculate what will be the pressure at the exit of HP turbine, we have correlation in terms of isentropic efficiency. Isentropic efficiency for the turbine it is given 91%. So, let us use this information. Based on that we will be calculating what will be our expansion ratio, and that is what will be giving us say HP turbine exit pressure as 819.37 kilopascal. So, this will be the exit pressure from HP turbine. We have similarly the component that is what is say LP turbine. This LP turbine which is used to rotate the fans. So, if we are correlating, that correlation will be in terms of mechanical efficiency, and this is the work equation for LP turbine, and on other side for the fan we can say it is 1 plus beta m dot core CPC T03 minus T02. So, based on that we will be calculating the exit temperature from the LP turbine, and this temperature is coming 993.81 Kelvin. Once we have this exit temperature, based on our isentropic correlation, we can calculate what will be the expansion ratio or pressure ratio for the turbine, and this pressure ratio base we will calculate the exit pressure from the LP turbine. This exit pressure is coming to be 390.2 kilopascal. So, up till here what all you have done for turbojet engine, what all you have done for all kind of turbofan engine, this calculation strategies that what will remain same. Do not get fed up with this is known to us. Just do practice. Without practice nothing will come, and these numbers they have the specific meaning, they have specific reason why they are like this. Okay, let us see what is the meaning of these numbers. So, now what we have is our mixing chamber, and for this mixing chamber, as we have discussed, we have two streams. One it is H03, second it is H07. First one that is what is from fan, and here this is what is my heat, that is what is coming from the turbine, and this will be my exit, it is say H08. Now, if we are putting our first law of thermodynamics, and if we are doing the heat balance, this will be given in terms of m dot Cp T03, and here this is 1 plus F m dot core Cp T07. Similarly, on the other side we can write down our balance, heat balance in this formulation. Now, here as we have discussed earlier, my Cp value because of mixing, that is what will be going to change. So, here dedicatedly specifically we are writing this as Cp suffix 8. Okay. So, this suffix 8 we can calculate based on the correlation as we have discussed earlier. So, Cp value for my hot gas is 1200 joule per kg Kelvin, for air it is 1005, my bypass ratio is 0.25. So, it says my Cp value is coming 1161 joule per kg Kelvin. Be careful, this is what is of need. Same way we need to calculate what will be the specific heat ratio. Now, this specific heat for hot gas it is 1.3 and for cold air it is 1.4. So, let us put this number, it says my gamma value is coming to be 1.32. Okay. Similarly, we can calculate what will be my gas constant R. So, this value if we are putting, it says my R is coming 287 joule per kg Kelvin. So, now you can say at the entry of my nozzle I have the information available. Now, based on this availability I need to calculate what will be the pressure and temperature at the entry of the nozzle or at the exit of mixing chamber. So, let us look at what energy balance we have written. So, based on our energy balance we can calculate the exit temperature. So, just do practice for putting this as energy balance, okay. And based on this balance it says my T08 is coming 903.22. So, this will be my exit temperature from the mixing chamber. Let us look at what is happening in terms of pressure. Now, as we have discussed, for mixing to happen we need to have the exit total pressure from the fan and exit total pressure from the turbine that need to be same. Just look at these numbers, say P03 we have done our calculation, that is what is coming 390.1 kilopascal, and here it is 390.2 kilopascal, maybe few pascals here and there, that is what is tolerable. Okay. But be careful, these pressures need to be same. Now, let us put this, if this is the case we can say our P08 it is given by P07 minus what is the loss in mixing, and this mixing ratio, that is what is given, it says 2% loss, that is why this mixing ratio is 0.98, and that is what will be giving the exit pressure from the mixing chamber, it is 382.4 kilopascal. Now, once the temperature and pressure, that is what is known to us, we need to calculate what will be the mass, that is what is coming out, because now we will be doing our calculation for the nozzle, and my total mass flow rate here in this case, you can say it is m3 plus m7. This m3, it is beta into m dot core, and m7 is m dot core into 1 plus f. So, that is why we will be having this total mass flow rate is 1 plus f plus beta into m dot core. So, that is what is the difference. Be careful. We have our single nozzle now. Okay. So, that is what. So, here in this case, since our total mass flow rate, it is given, it says 80 kg per second, our bypass ratio is 0.25. So, we can calculate the core mass flow rate, this is coming to be 64 kg per second. Once we have this core mass flow rate, we can calculate what will be the mass flow rate at the exit, and this is coming to be 81.50 kg per second. Okay. So, be careful, do not commit any mistake in this case. Okay. Now, since this is known to us, so we have information about the mass flow rate which will be entering inside the nozzle, we have information about the total pressure, we have information about the total temperature at the entry of the nozzle. Now, we want to calculate what will be the exit static pressure, what will be the exit static temperature, because that is what is required for calculating the exit velocity. Okay. So, similarly, what all we have done up till now, we will be doing our calculation for the critical pressure ratio. So, this is representing critical pressure ratio P08 by Pc. Since for this nozzle we have given the information, it is a 95% efficiency. Similarly, just look at this gamma is gamma 8, do not put that as a gamma h, be careful, this we have calculated and this value is coming 1.32. Okay. So, if we are putting this as a number, we will be getting our critical pressure to be 200.2 kilopascal. Now, we will be comparing that with the exit pressure. Our exit pressure is 101.325 kilopascal, and if we look at, it says my critical pressure is greater than that of my atmospheric pressure. So, my nozzle will be working under choke condition. Again, this all things in terms of choking, unchoking, we have discussed in week 2. So, those who are straightway moving towards week 8, just revisit week 2 for say the clarity and for understanding. That is the reason here, if we look at, my exit pressure will be equal to my atmospheric pressure, critical pressure, and that is what is say 202.200 kilopascal. Okay. So, if this is the case, we can calculate what will be our exit temperature, and this exit temperature is coming to be 778.64 Kelvin. Okay. And we can calculate our exit velocity. This exit velocity we are calculating, it is 1.32, 287, that is what we have calculated, and this is a 778.64. So, we will be getting our exit velocity 543.12 meter per second. Okay. Now, since we have information about the exit velocity, we can do our calculation for the thrust, and for the thrust calculation we know it is comprising of momentum thrust, momentum drag and pressure thrust. In order to calculate our pressure thrust, we need to do the calculation for differential pressure into area. So, my area is required for this case. So, let us look at what we know about this area calculation. So, area we know what is my mass flow rate that will be coming out from the nozzle, it is given by density into area into velocity. This mass flow rate we have calculated, V9 also we have calculated, and my density we can calculate, it is P9 by RT9. and if we are putting all this number, density is coming to be 0.89 kg per meter cube. All other informations are known to us because we have done our calculation in terms of mass flow rate. It is 81.50, velocity is 543.12 and density is 0.89. So, that will be giving the area to be 0.1675 meters square. Okay. So, let us look at how to do the calculation for the thrust. So, for thrust we can say this is my exit mass flow rate. Okay. So, it is m9, we can say m dot core into 1 plus beta plus f v9 minus m infinity v infinity. This is my area into this as my differential pressure. So, let us put all these numbers. We have m dot core as 64, beta is given 0.25, fuel air ratio we have calculated 0.0235. If we put all these numbers, my net thrust is coming to be 60.83 kilonewton. Okay. Now, the next component what we want to calculate, it is our thrust specific fuel consumption. That is what we are writing in terms of fuel air ratio into m dot core divided by thrust, and this number is coming 24.72 gram per kilonewton second. Okay. Now, we will be calculating our efficiency. Propulsive efficiency we are correlating in terms of V infinity into thrust. Since my V infinity is 0, so we will be having our propulsive efficiency to be 0. Similarly, when we are calculating our thermal efficiency, putting this as a number, we have our V infinity, that is what is coming to be 0. If we put all these numbers, the thermal efficiency is coming to be 18.67%. Now, the next component what we want to calculate is our thermopropulsive efficiency or say overall efficiency, where our propulsive efficiency is 0 and thermal efficiency is 18.67, that will give the overall efficiency to be 0. Okay. So, let us compile all this information what all we have done. So, based on velocity, pressure, temperature, we have calculated our exit area to be 0.16, net thrust it is coming 60.83, thrust specific fuel consumption it is coming 24.72, propulsive efficiency is 0, thermal efficiency is 18.67 and our overall efficiency is 0. So, here we are stopping with. In next lecture, we will be discussing about what will be the effect of different cycle parameters on the performance. And here what discussion we are doing, that discussion is mainly for say mixed flow configuration without afterburner. In next lecture, we are planning to have the numerical and discussion where we will be discussing mixed flow configuration with afterburner. Okay. I am sure you have understanding about what all we are discussing at this moment. Now, in order to have some clarity in terms of say your afterburner, it is advised that you just revisit say week 4, where we have discussed about the afterburner configuration. This afterburner configuration, that is what will be helping you in order to understand how we will be using those data for the mixed flow configuration. So, thank you very much. Here we are stopping with.